It turns out that each isotope of an element appears in its own natural abundance or percent compared to all the other isotopes of that element. Some of the isotopes are more stable than the other, and so they're present in a higher abundance or higher percentage on our Earth. So let's look, for example, at the three natural isotopes of neon. We have neon 20, neon 21, and neon 22, and their abundances are really different. Okay, the most abundant by far is neon 20. That is the most stable of the three isotopes. The other two isotopes of neon are present in much smaller amounts. So what scientists did when they were making the periodic table, they asked themselves a basic question. Which mass do we report for neon in the periodic table? If you don't want a periodic table that shows every single isotope of every single element, you need to somehow represent the conglomerate or the mix of isotopes. And so scientists decided to take an average mass of all of the natural isotopes of an element. So the question is, do we take a simple average of the masses, in which case we would get 21 for the mass of neon, or should we also take into account the fact that each of these isotopes is present in different abundances? Scientists decide that the overall average mass of an element should be related to how much of that isotope is present. And so they came up with a formula for what we call the weighted average atomic mass of each element, which averages the masses of each isotope, but also weights each of these masses by how much of that isotope is present. So let's look at an example. There is a formula that we use to calculate average atomic mass. Okay? And basically what it is the abundance of an isotope in fractional, that is decimal form, not in percent form, times the mass of that isotope. So if you look in the back slide, the last slide, you can see that the percentage of neon 20 was 90.48. So remember, this equation looks for the fractional abundance. So the fractional abundance of neon 20 is 0.9048. Okay? And the mass of neon 20, of course, is 20 AMU. That's for the first isotope. You do that type of math for each of the isotopes of an element. In the case of neon, there would be 3. The fractional abundance of neon 21 is 0.27. Its mass, of course, is 21 AMU. And then the third isotope of neon has an abundance of 0.0925, and its mass is 22 AMU. I want to take a moment to point out a really common error that students make. That third isotope, neon 22, had a percent abundance of 9.25. Be really careful when converting that to fractional or decimal abundance. Remember that anytime you go from percent to decimal form, you need to divide by 100, which means you need to move the decimal point over 2 places to the left. What I see a lot of students doing in a number like this is accidentally writing 0.925, which is wrong, instead of 0.0925. Just double check yourself on these very small percentages. It's really easy to accidentally drop a 0. So then what you would do to find the average atomic mass of neon overall as an element is you would complete this mathematical equation. And you would get the number that appears at the bottom of neon on the periodic table. Here's an example for you to try on your own. Turns out that chlorine has 2 naturally occurring isotopes, chlorine 35, chlorine 37, and use the formula that I just gave you for average atomic mass and go ahead and calculate the average atomic mass of chlorine. I would recommend stopping this video and then turning it back on to check your answer with mine. Alright, so using the formula for the average atomic mass, let's go ahead and see how we calculated that for chlorine. I would first like to point out that in a lot of these problems you might see the possibility of using two different masses. For example, they showed you symbols for the two isotopes of chlorine, chlorine 35 and chlorine 37. And so you might ask yourself, well, why can't I just use the number 35 in the formula and the number 37? Why am I using these really precise decimal forms? If given the choice in a problem to use a rounded value or a much more precise value, go ahead and use a more precise value. And since they gave those to you here in this problem, that's what you want to use. So again, make sure when you're plugging in for the formula average atomic mass that you convert the percentage abundances to decimal form by dividing by 100. When you calculate this through, again, carry too many sig figs until you get to the end. Don't round until the very end. You will see that the average atomic mass for the element chlorine is 35.45 AMU. If you look at the periodic table, that is the number that appears on the periodic table. One of the things you may not have noticed and that might help you in some of your homework, mastering chemistry homework, is the average atomic mass that appears in the periodic table will be closer in value to the mass of the isotope that is more abundant. Did that make sense? Let me say it one more time. The average atomic mass that you see in the periodic table at the bottom of each element symbol will be closer in value to the mass of the isotope that is most common or most abundant. So what you can tell by looking at the average atomic mass of chlorine is that of the two isotopes of chlorine, the isotope chlorine 35 is the most abundant because the average atomic mass is closest to the 35. That's just kind of an important, useful little tidbit to have. That's it for this lecture.